we start the continue with our topic. So just to refresh your memory, what we did last time and where did we stop? So basically, we talk about the three design styles. So we have data flow, we have structural, and we have behavioral. And then we can mix between those three, but those are the main design styles. So the data flow, of course, we said based on your circuit, you need to choose one of those design styles. And sometimes you need to mix. You will see some examples later on. Once we cover sequential circuits, you will see that sometimes you need to mix. Data flow, we said we use concurrent signal assignment, and we have three. We have simple signal assignment, which we covered, and we have conditional signal assignment, and we have selected signal assignment. We did the three. We covered them, we showed you examples. So for example, the last two, we did an example for a multiplexer. So all they are concurrent signal assignments. What I mean by concurrent, when you put them in a VHDL code, it doesn't matter which one will you write first, because they will run in parallel. Structural, we said this design, and sorry, for the first one, we say this design style is good for combinatorial circuits. So all circuits that we did so far, the ones that you did in the lab, this is the best design style for them. Data flow. Of course, you can use the structural or you can use the behavioral to do it, but it's not the best one. As I said, the best description is the one that has less lines. If I can describe it in 2 lines, I don't need to write 10 lines to describe my circuit. The next one is structural, where we said component. And I gave you the example where you can use this. So we have, for example, if we have a circuit that includes, let's say, 3 components, 3 copies of the same components. Let's say a component A. I don't care what is A. So it could be an AND gate, it could be a multiplexer. So this is the same component. So it's one component. We have one component used 3 times. And you need to understand this. We don't have 3 components. We have one component, which is A, used 3 times. So in this case, with this design style, and this is what I'm going to cover next in the next slide, we write one VHDL description for the components for A. So if it is an AND gate, you just write a code for the AND gate. So you will be using here, for example, data flow. And then you write another VHDL code for the whole circuit. Let's say I call this circuit B, which includes 3 components. So I need one VHDL code as well for circuit B. So which means I will be having 2 VHDL codes. One is for the component and another one for the big circuit, which is B, that includes 3 copies of my component. In this second VHDL code, I don't need to repeat the code for the components because I already have it. I just create instances. We say instances of that component. So I have 3. I need to have 3 instances, so 3 lines in my code. And in those 3 lines, I will just show how those components are connected together into the input-output ports of circuit B. So this is all what I need to show in the second VHDL code. So we will be having 2 VHDL codes. Is this clear? So this is how we work with components. And then the third one is the behavioral design style. And we said this one is good for, here we use a process. So I will explain what is a process. And inside the process, we use what we call sequential statements. So we'll explain what is a process, how does it work, and then how do we use sequential statements inside the process. So this is what we will cover. So next, I'm going to talk about components and how do we use them in structural design style. And then after that, I will do process. and then sequential statements, and with examples, how do we use them in a behavioral design style. So behavioral is good for sequential circuit. You can always do combinatorial circuits with it, but it's not the best style. The best style is data flow. Components, the structural, as you can see, you can mix. I mean, you may have a component where you will use the data flow to describe it, and then here you use the structural. In the second VHDL code, you use the structural design style. So we'll explain all this in the remaining slides. So if I go back to, I think we stopped here. So this is for components now and instantiation. I already explained this, that you will need a component, and then you need to create instances of that component. So remember, here, now in this example, if I have, let's say I have a circuit A, and then I have here B, and this is circuit C. Of course, those will be connected, and there will be inputs, outputs, ports, and those all will be connected. How many components do I have here in my circuit C?
6 components.
Huh?
6 components.
No, it's not 6. I mean, I was explaining just a few minutes ago. Be careful.
We have 2 components.
Sorry, 2.
How many components do we have here?
We have 2 here we have 1.
We have 1. I said we have 1 component used 3 times. So it's not 3 components.
Yes.
And I said be careful. And now I'm getting the same mistake that, how many components I have here? I have 2 components. Good,
yeah.
Excellent. So I have component A and I have component B. Component A is used 4 times. Component B is used twice. And that's it. So 2 components. So be careful. This is what we mean by a component. So it's not instances of that component or copies of that component. Right. So I'm not going to. I told you we need to write the code for the components first. I think you know how to write this. I mean, for example, if it is if you need to use data flow, we already did data flow. So if the component is a multiplexer, I already showed you an example how to. This is a multiplexer. So you write this code. So first you write the code for the component, and then we need to use it in the second VHDL file. So you create another VHDL file. In the lab, when you work with this, you create a project, an FPGA project, and then you add 1 VHDL file first. You describe your component. Once you are done with the component, you can check it, you can simulate it, you can test it on its own, and then you create another VHDL file for the bigger circuit. And this, what I'm showing here, the template that you can see here, is the one for the bigger circuit, because I assume you know how to write the code for a component. And in this, of course, this is a normal VHDL code. It has an entity. So in the entity, you describe the inputs and outputs of your circuit. And then you go to the architecture. In the architecture, the first thing that you need to do, you describe or you declare. We are not describing because we already described the components in a separate VHDL file. So you have the description already in one VHDL file. Here, you just declare, because in one project, one big project, you can have hundreds of files, and then you can select components from the files. How does the compiler know that, okay, you need to use this specific component? By declaring the component here. How do you declare it? You have the entity, right, for the component, for the other VHDL file. You just take the entity as it is, copy, paste. You remove the keyword entity, you replace it with the keyword component, and that's it. The rest is the same. And of course, you add components here. You add components here at the end. So this is basically the entity that you have in the other VHDL file with the exact name. So you don't need to change the name. And this will link this VHDL file to the component. So the compiler will understand, okay, so you want to use the component that is in this VHDL file with an entity named with this name. And it's very important to keep the same order of the ports here. And this is another mistake that many students they do. Until now, I cannot understand why, because I always tell them, copy the entity and paste it. When you copy paste, you don't change anything. You just change the name entity with component. But students, they don't do this. Some of them, they just go and they try to rewrite the entity and rewrite. For example, in your VHDL file, and this is what I'm trying to, let me explain it in, let's say that this is my circuit. Right. So this is my circuit. I have two AND gates. Of course, the best design style here is combinatorial. It's just one line. C, or A, B, C, D. So D is equal, or just equal A and B and C. That's it. This is my code. Let's say that I want to do it now with structural, which you can do, but it's very bad idea. But just to show you now, we just work with small components for you to understand. How do you do this port mapping? How do you connect the components and so on? So the first thing that we need to do is what? As I explained. The first thing that we need to do.
Describe the identity.
Describe the AND gate. So we have the AND gate here. This is a component. AND gate has two inputs, one output. So I can start with entity. I can name it AND gate. We have is and then port, and then we start placing our ports. Here I can use A, B, C as my port. Yeah, this is my component. It's two inputs, one output. So A, small a, B, or I can use X, Y to avoid any problem with X, Y are inputs. So this is X, this is Y, this is Z. Is an input, of course, STD logic, and then we have Y as an output, STD logic, and so on. And then I finish my entity. And then you write the architecture, right? So, and then we start the architecture and you describe the AND gate. So this is code 1. I'm done with it. Now I need to go and create code 2 for this big circuit. Code 2. What is the entity for code 2? Of course, I will need to start with the entity. I give a name, is, and then port. So what is the entity for code 2? What should be the entity for code 2 for this big circuit?
Copy and paste code 1 and change the entity to component.
No, I'm talking about the entity for this circuit. What you've just said is later in the architecture when we declare the component. Forget about the structural design style. If I ask you to write the code for this code 2, how do you write it?
Z and C are inputs and Q is the output.
Which one are input?
Z and C.
We don't have Z and C.
X and Y.
We don't have X and Y. X and Y are in the AND gate. I don't. Do you understand my question? No, forget about the components, and I ask you to write the code for this one. Write the code for this one. A, B, C, D. What is the entity for this one?
A, B, C is the R inputs.
Yeah, A, B, C are inputs, and is the outputs. This is the entity that we need here. We need A, B, C are inputs, and D is the output. I think it's very simple. This told you we need first to write the code for the AND gate, the component. So I put it here in red. Sorry, this in red. So if I take this component, I have two inputs, two outputs. If I think of this as a black box, I start with the entity. I have two inputs, one output. Now I'm going to move to the bigger circuit, where I need to use two instances of this AND gate, two copies of this AND gate. I need to start with the entity. What is the entity for the big circuit? Is this one. We already have it. So is this is my entity. And then I go to architecture. And inside my architecture, I need now, because I have components, I need to use a component. Here I need to declare it. To declare the component. Here we copy this, we paste it here, as I said. Copy, paste, and then replace entity with. Do you understand what I mean by? So we have two entities. One is for the component, and we have the other one for the big circuit. And then, if we continue, and this is what I mean here by this syntax. So this entity is for the big circuit. I'm using the word big circuit to understand that the circuit that includes all components. And then we move to declaration of the component. Now it depends if you are using two components, and I already explained what I mean by one component, two components, right? So I'm not talking about the number of instances of the same component. So if I have in my circuit I'm using two components, I need to declare both of them. And this is what I put, for example, here. So I need to declare the two. So I go to the VHDL codes of the components, copy the entity and place it here, and then use it. And then once you declare the components that you need to use, you just, if you have two copies, you need to have two lines here. We call this the port mapping. So basically the port mapping is just to show the connections. So for example, the X and Y that I showed you for the previous example, the AND gates. So port X is connected to what? Port Y is connected to what? Port Z is connected to what? You do this for the first instance of the first copy of the component. And then you move to the next copy of the component. And then again, for the next copy of the component, X is connected to what? Y is connected to what? And so this is what you do here. And that's it. You just show how the parts are connected. So let's do a simple example here. I put here let's say that I have circuit B that consists of two copies of the same component, which is A, component A. So I need to write the code for component A first. I don't care what is component A. You know, to explain how structural design style work, you don't need really to know what does the circuit do. I mean, if you have the code for the component, all what you need is just the entity and the connections, how the ports are connected. This is all what you need. You don't need to know how does the component work. Right. But as designer, I mean, you should know, of course. I mean, if you are asked to design the component yourself, then you should know. Right. So let's say then this is the code for, I think the code for component A is clear. We have two inputs, one output. I don't care about the architecture. It could be anything. You can think of this as an AND gate. You can think of it as an OR gate. You can think of it as any gate. And then we move to the second VHDL description for the big circuit B. So we have the entity for circuit B. As you can see, we have B1, B2, B3, B4 are inputs. B5 and B6 is an output. I have one component A, so I declare it here. So what I did here, basically, I copy this, paste it here. Copy, paste, and then delete the keyword entity, replace it with component, and delete this one and replace it with component as well. And this is very, very important. The name of the component here should be the same as the one that you used here. This is very important. You are not supposed to change anything. Even the order of the connections of the ports. So here, when you write the code for the components, you put A1, A2 input, and then you did A3 as output. Another student can choose to start with the output, A3, and then do A1, A2. This is fine. But once you have it, you described it here, you are not supposed to change it in the second VHDL code. You have to keep exactly the same order, because this is very important here when we do the next step for the connections. Is this clear? So this is for declaration. Now we will move to the most important part, which is the connections. How you need to create instances of the components. How do we create it? The first thing that we need to do is sorry, delete this space so I can have some space here to write. So we start what we call with the label. This is just a label, a name that you give to. So I started with B1 to say this is the first component in this circuit B1. You can name it, you can give any name. And then what follows is very important, is the name of the component as you declared it here and as you used it here as well. And then followed by keyword port map. Port map, which means we are mapping the port, or we are connecting the port. And then, now, how many ports do we have in my component? How many ports do we have in this example?
Six.
Ports.
How many ports do we have in the component?
In the component, we have 3.
We have 3. Component, we have 3. We have A1, A2, and A3. A1 is the first one. According to the syntax, I can write it this way. So I start with A1, and then I use this operator. A1, this means A1 is connected to what? Of the first component, this one. So we start with this one. This is 1, and then we go to this one, 2. So we start with 1. A1 of the first component is connected to what? Or the first instance, or the first copy?
B1 and B2 and B5.
A1 is connected to what? A1 is connected to what? B1. I'm asking about A1. So A1 is connected to B1, comma. A2 is connected to what?
B2.
B2, good. And then comma, and then A3 is connected to what?
B5.
B5, good, excellent. That's it. We are done with the first one. Those are optional, you know, A1, A2 are optional, so you can remove them if you want, and you can just write, and this is what I put here. You can just write B1, B2, B5. And this is why I told you the order is very important. So if you put A1, A2, A3, then you have to keep it here as it is, because the compiler, if you use this, the compiler will take A1 is connected to B1, A2 is connected to B2, and A3 is connected to B5. And then we'll repeat the same for the other component. I will do exactly the same. So I will have a different label, and I will do the port mapping for the second copy of the component. For the second copy of the component, so I used here B. I named it B2, and of course you keep the same name, and then port map, and then the port. So A1 is connected to what? A1 of the second component, of the second copy of the component.
B3
is connected to B3. A2 is connected to B4, and A3 is connected to B6, and that's it. I'm done. And be careful as well. The first here are inputs, B3 and B4 are inputs. They should be connected to inputs. As you can see here, A1 and A2 are inputs. They should be connected to inputs in your circuit, or to signals, because a signal could be input or output. if you have an output, it should be connected to an output. So B6 is an output and A3 is an output. So if I put B5, oh sorry, B3 here, I will get syntax error because B3 is an input and you cannot connect an input to an output when you do the port mapping. Is this clear? So let's do another simple example. Let's have this circuit. Again, what is the best design style for this circuit?
Data flow.
Data flow. We can just write Q is equal S and not Q. And then we take, NOR. This is a NOR gate, yeah? And then we can take NQ is equal. And of course, and this is very important. Do you see here this is an output? And then we are taking it as an input as well. So this is a good example where we can say, we can declare it as in out. So it is an output, but we are taking it back as an input here to this gate. The same for Q. It's an input and we are taking it as, it's an output and we are taking it as an input. So this Q and NQ can be declared as in out. Right. So we want to use, as you said, data flow is the best one, but just to show you an example with component, the NOR gate is so I have two NOR gates. This is NOR gate 1 and this is NOR gate 2. Now, what do we need to, how do we start first?
Describing the NOR gate.
Describing the NOR gate first. We need to describe the NOR gate, entity and architecture. And then we move to the component. So for this component, what are the inputs and outputs? Oh, sorry, for this circuit. What are inputs and outputs?
SR.
S and R are inputs. Good. And then
The
have
output.
Q. We have Q and Q as in out. You can have them as in out. You can solve the problem with outputs only, but you need to declare signals. But let's do it. It's easier to work with in out for now. So this is what you said. We have the code 1, and then we have code 2. Code 1 is the simple NOR gate. I think it's easy. Now, and then I need to copy, paste here, and just replace component, the keyword, the entity with the keyword component, and that's it, right?
Doctor?
The entity, we already talked about it, so we have 2 inputs and 2 in out. Yes?
Doctor, here we work with the structure style.
Just giving you, we are talking about structural. I'm telling you, this is not the best style for this one, but then just to explain again, how does the structural work? So it's easier for you and easier for me to explain it with simple components.
Yes, but I mean here in this example, we do it by structure.
I'm doing structural here, right? Do you see we
Yeah.
have 2 codes? If
Okay.
it wasn't structural, then I wouldn't have 2 codes. I will have
Yes.
only 1 code. If it's data flow, I mean, this is what we started with. We started that what is the best design style here is data flow. And when we do data flow, you just write this 2 lines in 1 code, and that's it. We are done.
Yes.
But I told you, because I'm covering components, let's do it with components and show you how to work with components. Another example, just for you to understand. So this is structural. We create the components first, and then we do the rest. Now we declare it, as I said, and then next we move to creating instances of the component. So I have 2, 1 and 2. This is why I need 2 lines. You have 2 copies, you need 2 lines. You have 10, you need 10 lines. How many inputs, outputs do we have in my component? How many ports?
Two
We have in the
inputs and
component?
output.
Yes, we have 3 ports in total, 2 inputs and 1 output. I need to see 3 here. And this is another mistake, which until now I couldn't understand why the student they do this mistake. Two common mistakes. You have 2 instances of the component, so you see sometimes just 1 here. I don't see the 2 lines. And the other mistake, you have, let's say, 3 ports in the component. When it comes to the port mapping, you see 2 or you see 4. I don't know from where they get the extra ones, or they reduce the other one. So, and these are common mistakes. So be careful. I'm talking about the order of the port and the number of the port. You're not supposed to change them. Once you have the code here, then that's it. So we start with the first one. So A, input A of the first NOR gate is connected to what?
S.
Is connected to S. So we have S here. B, input B of the first instance of the component is connected to what? Is connected to NQ. No, it's not connected to R, it's connected to NQ. How do you see R? We are still here. We are still working here.
Okay.
We are still here. We are trying to connect this component. So A is connected to S, B is connected to NQ, and C is connected to Q. So this is what I put here. So you need to finish with the first component. Oh, sorry, with the first copy of your component. Now we move to the second copy of the component. A is connected to R, B is connected to Q, and C is connected to NQ. And this is what I have here. And that's it. This is the circuit. Is this clear?
Yes.
Yes, doctor.
Yeah. So, and be careful, as I said, to the points that I mentioned. Right. Now, this is the structural design style with component. Of course, as I said, here we work with 1 component only. In some circuits, you may have more than 1 component. In this case, you need to declare them here, and you create instances for the components here, and that's it. And you show how they are connected. We will do this in the tutorial. Right, now we are going to move to the last design style, which is the structural design style. So in the structural design style, we said that a process, you need to use a process. It's not like in C++, or for example, if you want to use a for loop, you just write it in your code inside the main, and you write the for loop. You cannot do this in VHDL. This has to be inside a process, and this is how you create a process. So again, it starts with the keyword process and ends with end process. There is a label here that you can add, which is optional. You can put a label for your process. And then we have as well the sensitivity list, which is optional. And then declarations section. Do you remember when we talk about architecture? The process will be inside architecture. So we have architecture, and then we have begin. Here we call it declaration for declaration part for architecture. And then let's say that inside the architecture, you need to use a for loop or whatever. You need to have a process first, and then end process. Inside process, we have as well begin. And here between process and begin, you can have declarations. Those declarations can be used only inside the process. So basically, they are local to the process only. So you can have a constant, for example, here declared here that you can use here inside the process. Outside the process, you cannot use it. if you need any declarations to, or anything to be used inside the process only. And then you finish with, you add your statements here, which are sequential statements. Right. What is this sensitivity list? The sensitivity list is the list of signals to which the process is sensitive. Let's switch to here. So we said a process. So for example, when you write a process and you put A, and A is an input, let's say A is an input in your entity. A, you have a circuit, and you have A here is an input, so it's an input in your circuit, and inside the process, and then you do begin, and then I can, for example, write if A is equal 0. This is the sequential statement, if statement. Then do something. We don't care. Just to explain and if and process. This is a simple process, simple example. So this will be inside the architecture. I put here A in the what we call the sensitivity list. So in here you can put input or signals. Input ports or signals can be placed in the sensitivity list. So how does it work, this process? The process will be pending here, will be waiting until there is a change on A. Let's say that this A is connected to a switch. At time t equal t0, A is 0. We keep it 0. There is no change on this input. We don't change the position of the switch. We keep it there for, let's say, one minute. And then after 1 minute, we change it. During that minute, before we change it, the process is waiting here. It will not execute this. This will not be executing. So waiting until there is a change on A, or any signal that is in the sensitivity list. If there is a change, so if A changes from 0 to 1, time t is equal t1, it changes, then this process will be executed entirely from beginning until the end, and then it will loop back and wait again for A to change next time. Do you understand? So this is how the process works. It's pending.
And Doctor, it lacks a loop.
Huh?
It's a loop.
It's not a loop. A loop is always executed as long as the condition is true. So for I is equal 0, I is equal 1, it will be executed. This process will wait. It loops, yes. Once it finishes, when it finishes the execution, it loops back. Yes, it does a loop, but it does more than that. It waits as well until there is an event, a new event on A. So the process will be triggered by A. It will not execute until there is a change on A. So if A is 0, changes to 1. In this case, the process will be triggered and statements inside the process will be executed entirely, and then it will loop back, and then it will wait again. If A stays 1 for the whole day, the process will be waiting here. Those will not be executed. Do you understand? This is how the process works. Is this clear? Yes or no?
Yes.
So the process waits. It doesn't execute until there is an event on A, until there is a change. What we mean by an event, there is a change. The input changes from 0 to 1 or from 1 to 0. There is a change on it. Then it will execute the statements inside. And then when it finishes with the last line, it goes back to the beginning and wait. I hope this is clear. And one important point as well about processes, you can have more than one process in your architecture. So let's say that I will call it P1. So I have a label, I can use a label P1 process. And then I put A, and then begin, and then I will have statements here, and then end. So this is one process. And then I will have another process, P2. Process, and let's say that I have another variable B or another input, begin, and then I will have statements, and then end process. So this is the second process. So I have, let's say I have two processes in my code. Those processes, if you write this in a C code, this is how the execution will be, one after the other, sequentially. So we finish with the first one, and then we go to the next one. And this is not the case in VHDL. So those two processes will run in parallel. So you can consider a process as a block, as parallel, as a concurrent statement, like the other concurrent statements that we covered. But once it starts the execution, things inside the process will happen sequentially. This is why we call them sequential statements. So basically, if I may represent it with a block diagram, so you will have it like this. It will run in parallel. P1, P2. So process, this one is waiting here, this one is waiting here, and they will run in parallel. Let's say at the same time, A and B will change at exactly the same time. So at the same time, both processes will be executing their statements. So they will execute here inside sequentially. But they will start at the same time, and the things will happen in parallel. So they are like two blocks, two hardware blocks in our FPGA. Is this clear? So the process as a block is like a concurrent statement. And this is very important. Right, I think I was explaining this. There is an example here. For example, with the process. As I told you, the circuit, the best style is data flow. I think you know this now. Yeah, this is data flow. But as I can do it with structural, I can do it with sequential. With behavioral, if I want. But of course, this is not the best design style. If I do this with a process, the inputs, so the output D depends on A, B, and C. If I want to use an if statement, I think you know the if statement, so I'm going to give the example with an if statement. So I can use an if statement here to implement this. I cannot write the if statement on its own. I have to put it inside a process. So this is a process. So I put the if statement inside the process. And in the process, the sensitivity list is A, B, and C. I want this to be executed, of course, when one of the inputs changes, right? If A changes, or B, or C, or both two of them, or three of them, they change, we need to update D. We need to check what is the new value to update D, to have the new value for D. So this is why I need to include them all in the sensitivity list, A, B, C. And then I can do it with an if statement here. I can have this condition. If A XOR B XOR C is equal 1, then the output is 1, right? Then D is 1. Else, if it's false, then D is 0. So the output will be 0. And that's it. So I can do this with a simple if statement. Right?
Please.
Yes?
Why you use here if?
Just to show you an example with the structural design style. sorry, with the behavioral design style, just to show you how to use an if statement inside a process. So this code basically will describe this circuit. So if I give you this circuit and I tell you do it with, as I said, we know that data flow is the best. But if I ask you, okay, do it with structural design or behavioral design style. If I ask you to do it with structural, you should know how to do it with structural now. So you describe this as a component, and then you have the other bigger circuit, and you segment code and you do the port mapping. You know how to do it, right? If we ask you to do it with structural. You know.
Yes.
Now I'm asking you to do it with behavioral. Although it's not the best one, yeah, as I said. So with behavioral, I know that I need to have a process. So I put a process, and I know that the output D depends on A, B, and C. So I put those A, B, C inside the sensitivity list. And then one solution, this is not the only one solution is to do this, to check if A XOR B XOR C is equal 1, this is a condition. If this condition is true, if A XOR B XOR C is equal 1, this means D is 1, right? Because this is what is D. D is equal A XOR B XOR C. This is D. So if A XOR B XOR C is equal 1, then D is 1, else D is 0. And that's it. This describes this circuit. Again, it's not the best one, but I'm just to show you an example how to work with a process. And for example, if statement. Is this clear?
Yes.
Yeah, and again, this is not the only solution. You can have different solutions.
Yeah, I can do it without condition.
Without?
I can do it without condition, without using if.
How do you do it without an are you talking about the process, using process? Yes, we can do it without condition. We can do it with D is equal A XOR B XOR C. You cannot write this as it is inside the process. Inside the process, you can use only sequential statements. This is not a sequential statement. This is a simple signal assignment. A simple signal assignment, you cannot use it unless it is inside a sequential statement, an if or for loop or while or so on. We are going to talk about them later. You can do it without the process, of course. You just delete all this and you just push this line, and this is data flow. This is data flow. So, and this is the best one, the best answer, one line in your code. I don't know if you get my point, what I want to do here. I'm just trying to show you an example how to use, because this design style is good for sequential circuits. We didn't cover yet sequential circuits. I cannot show you a sequential circuit now and show you an example with process and if statements, because you will be lost. You need to understand first a sequential circuit, and then we explain how to describe it. I'm just trying to use what you have learned to explain things now, which you are going to use it later for advanced stuff. Here, this example is just to show you how to use a process or how to use an if statement inside a process. That's what I'm trying to do here with a very simple example. Is this clear? So, for example, if I ask you to do AND gate with, this is an AND gate, and I'm asking you to do it with structural design style. Oh, sorry, behavioral. How do you do it? I know data flow is the easiest. C is equal, sorry, I don't know why this, C is equal A and B, and we are done. That's it. This is the solution. Now, I'm asking you in the question, which I can give in an exam, do this with structural designs or behavioral, sorry. For behavioral, you know that you need to use a process. It's clear, right? When we say
Yes.
behavioral, automatically there is a process. So you need to
Yes.
use a process. How do you do it? And all of you should answer the question because you have the code in front of your eyes here.
We can make the process A, B, C.
We don't have C. We have A, B, and that's it. In the process, we don't put outputs.
Yes. Okay.
C is an output. We don't, the output, we will get it. So this is what we are trying to do. So well, we need to put only inputs inside the sensitivity list. So we have A, B, and then here I will just do if A and B is equal 1, then the C is equal 1, else C is equal 0, and that's it. And this will give me an AND gate. This is an AND gate. Again, I'm just showing you how to use them, to use the process, to use the if statement for a simple circuit. And you will apply this later to sequential circuit when we cover sequential circuit. Right, so these are the statements, sequential statements that you can use inside the process. We have the if statement. I already used it here, but I will give you more details about it. I think it's the syntax is a little bit different from the one in C++, but it's the same statement. I mean, it does exactly the same job. It's just the syntax. We have the case statement, which is similar to the switch statement in C++, and then we have the loops. We have for loop, we have while loop, and we have loop, as we pronounce loop. So we have as well loop. We don't have this in C++, but we have it in VHDL. Here, the while loop, we will do this. Do you remember when we talk about design steps in VHDL? Or when you write VHDL, the next step is to do simulation. So when we do simulation, you need to write another code, another VHDL code, which we call VHDL test bench. In this VHDL test bench, we include our test cases. For example, if it's an AND gate, we put 0, 0, 0, 1, 1, 0, 1, 1. We can specify for how long we want to keep it 0 and so on. So we will have a lecture about this. So there is a VHDL test bench. So the while loop is used in VHDL test benches, not in a normal VHDL code. So far we are talking about the normal VHDL codes. So the while loop is used inside those test benches. Right, if statement. Do you remember this? We did it with L, M, and N is the same function. I'm just changing A, B, and C. The if statement, this is the general syntax of the if statement. So we have if, there is a condition, then, and then we have statements. So and then what follows is optional, which means I can write an if statement like this. If condition 1, then, and then we have statements. I'll just put S, and if. This is correct. I'm following the syntax. You may have multiple conditions to check. In this case, you can add else if, else if. So for example, I can do if C1, then condition 1, then I will put statement here, else if condition 2, then, and then I can put statements here as well. I can finish with else, then, and then I put statements, and then and if. So it depends what you want to do. You may have multiple conditions. You may have just one condition to check. And then you can end with else here, which is the default one here. Else, those statements will be executed. So if none of the above conditions are true, then the last one will be executed, and so on. So there are different ways to write the if statement. So if I ask you to write the VHDL code to do this with else if, So how can you do this? So we can check, for example, this is an OR. We can check if this one is equal 1. If this part only is equal 1, then f should be 1, right? Because this is an OR. If this part is 1, then f should be 1 as well. Else, if none of them are 1, then f should be 0. But again, this is not the best solution. The best solution, we already did it in the when we talk about combinatorial, when we talk about data flow. We did the same example with LM and N, if you remember. So this one is the best design style. But here again, just to show you how to use if statement with else if. So, and this is what I'm doing here. So I can put the condition in this form. If A is 0 and B is 0 and C is 1, then it will give me 1 here. Or I can put it if A, if not A, and not B, and C are equal 1, is the same condition basically. Doing this condition or writing this way, it gives you the same answer, the same result. So basically this example just to show you that you can have multiple conditions. If, else if, else if the first two are not true, which means they are false, then f is 0. So this is another example with a process, and here we have 3 inputs, A, B, and C, and this is what I put in the sensitivity list, A, B, and C, right? Now, this is another example, and I did this in purpose, just can I access one line in the bus. This is the multiplexer. You know the H21 multiplexer. We have separate lines, 8 separate lines. But one of you can, for example, decide to put it as group them together. So we put D, data in is 8, is a bus of 8 lines. If we do this, and then we want to use if statement, again, we did the multiplexer, and so the selected signal assignment or conditional signal assignment are the best to describe the multiplexer. We did it. Now, if I want to use it with the if statement, and assuming that group those together, I will declare them as just one input, but with 8 lines. So in the previous examples, we declared lines separately. We have D0, D1, D2, D3. Now, if I want to group them in one, I call it D or data in, and I declare it as 7 down to 0. Now, if I want to access, so of course I can do it with an if statement where I will do if select, for example, is equal 0, 0, 0, then this is how multiplexer works, right? Then the output, if I call it O, is equal to the first line, right, in the bus. How do we? Using the number of the line between parentheses starting from 0. It's like what you do with an array. If you have an array of 10 elements or 8 elements, you do A0, A1. I can do exactly the same with the lines. If I have a bus, if I want to access one line of the bus, I can just do it this way. And then I will continue, else if, and then the next condition, select is equal 0, 0, 1. And I will list all 8 conditions until I finish, right? And this is what I wrote here in the code. So this is what I was talking. It doesn't matter with which one you start, as long as you include all the statements. Of course, this will be tested first, and then next, and then next, and then next, and so on. So it will be sequential, but it doesn't matter which condition you put first. as long as all of them will be there and all of them will be checked. So to do this, of course, we have a process. The output, this MX output will depend on the inputs, data in, and it will depend on select. So this is why we put the inputs in the process sensitivity list. And then I list all conditions until the last one, else. If none of the above are true, we just assign 0 to the output. Is this clear? If, else, if, else, else, if, else, if, else, if, until I finish all the conditions. Is this clear or not?
Yes.
Clear.
Yeah. Remember, we always need to start with a process. I cannot use if on its own. It has to be always inside a process. Right. Case statement, as I said, is similar to switch. So we use the case if we have clear cases, you know, or values for based on a, for example, the multiplexer, the select. So the select will have 8 possible values. So those are the 8 cases. So I can use this case statement here using this syntax, and we can use the keyword orders like what we did with the conditional unselected signal assignment. So it's similar to selected signal assignment, but the other one is concurrent. This one is sequential. So it needs to be inside a process. And then we just start our case, and then here select. Based on the value of select, the outputs will have different values. So 1, 0, 0, and then we can assign data in 0 to the output. 1, 0, 0, 1, we assign data in 1, and so on until we finish all 8 cases, and then I can finish it here when others. So which means if none of all those cases is true, then we just assign 0 to the output, similar to what we did here. If all the inputs are false, sorry, all the cases are false, or that the conditions are false, we assign 0. So again, we are doing exactly the same thing, the same job with 2 different statements. We have if and we have case. Someone is not muted, so can you please mute yourself, or if you want to talk, can you ask your question? Right. Of course, we can mix inside the process. I can have multiple statements. I can have if, I can have the case, I can have loops. Let's say now the same multiplexer that we did here, I added to it a chip enable, a line, an extra input. We call it CE. And the CE will enable the multiplexer. So if it is enabled, so if its CE is 1, the multiplexer works as normal, as what we did before. If CE is 0, then the output is always 0. We don't care about select, we don't care about data in. It will be always 0. So, of course, we need to add it into the entity. So we have CE, we need to add it to the entity. And then we write the code. So we ask you here to use if and case together. So there are multiple solutions. We can start with if. We use the if to check CE. So if CE is equal 1, then we can have the case statement to do all the cases that we have. So this code, all this code can be here. If CE is 1, else, this means CE is not 1, then the output is 0. And that's it. And that's what I put here. Of course, it's very important to add CE as well to the sensitivity list because it will affect the output. If we don't put it here, the multiplexer will not be, the process will not be triggered, will not be executed if there is a change on CE. So we need to include it. And then if CE, then we have this whole case, else we have the output is 0. Of course, here I can have another if statement instead of putting it here. I can have the other if statement, this one. This one can be here. So one if inside an if statement, which is fine as well. You can do it. So basically what I want to say here, inside the process, it doesn't mean that you need to have only one sequential statement. You can have multiple sequential statements depending on what you want to do. Is this clear? Now I'm going to move to loops in VHDL. So as I said, we have the for loop, which is very similar to the one that you know in C++. So those are the syntax, general syntax for them. I'll just show you some examples for each one. So for example, if we start with the for loop, so we start with, you can have a label, which is optional. And then you start with the keyword for, and then this is like the loop variable or the counter. So this will be like an integer. You can start from 0 going to 9, or you can do, for example, 9 down to 0. So you can use 2 or you can use down to. So here we start from 0 to 9. So which means we will have how many iterations? We will have 10. Going from 0 to 9 is 10 iterations. And then we do a, so for example, let's say that A is an array of 10 elements. It's a variable. It's a variable. Do you see here? I used equal. This equal. This means this one is a variable. Is not a signal. Remember this, yeah. So AI. This is a loop, for example, to initialize all elements of A to 0. So A is an array. I have 10 elements. So I do A0 is 0, A1 is 0, A2 is 0, A3 is 0. I don't have to write 10 lines. I can do it in a loop. And then I can just use AI is equal 0. And I will start from 0 to 9. I think you know the loop, so I don't want to waste time here. It's just, it's a little bit different, the syntax, but the logic is the same. What we can do with the for loop, we can do it with a while loop, but here in the for loop, the I is incremented automatically by 1, which is not the case for the while loop. So for the while loop, you need to take care of the incrementation. And then here, the for loop take care of the checking that if it reaches 10 or not. So if we do 9 and then 10, it will stop. The while loop, and we need to have the condition ourselves, so we need to include it. So this is the main difference. The while loop, you need to take care of the condition when to stop, and to take care of the incrementation of your variable or your loop variable, the I here, for example. So we need to increment it, which we don't need to do in the for loop. So we are doing exactly the same job here. We are assigning 0 or initializing all elements of A to 0 with a for loop or with a while loop. The while loop, we need to include a condition, and we need to increment the counter. Otherwise, it will not be incremented. I think those you know them. I don't want to spend time here. We have as well the loop, this one. The third possible thing that you can use for loop is loop, by just doing this. As you can see here, there is no condition, there is no starting point, ending point. So it's like if you write it as it is, it's an infinite loop. It will be executed forever. Now, if you want it to stop at time, you can always use this exit statement. So exit statement works with loop. you can have it inside the loop. So you can just write exit. Whenever this is executed, it will exit. There is no condition. You can write exit when, and you put a condition. So you can add the conditions within exit. So for example, here I'm using loop, and I'm putting here. So this will be looping. It will be executed continuously until this condition is true. Sum is more than 100. Do you see we are incrementing sum here? We keep incrementing until it reaches 100. So we exit this loop when sum is more than 100. I'm just using exit, but I'm adding an if statement. So you can always add a condition with an if statement. If sum is more than 100, then exit. So you can write it this way. So the condition could be within the exit statement, or you can add an if statement, and then if it is true, just write exit, and then it will exit if the condition is true. So the exit can be like a statement inside the if statement. So you can use different ways, you can use it in different ways. Right. I think the time is over, but I will just continue for 5 minutes just to summarize. Now I think we are done with everything, just summary of what we have covered. So we talked first about data flow modeling style, and we told you this is the best design style for combinatorial circuit. For example, this one. We told you that you can use simple signal assignment, conditional signal assignment, or selected signal assignment. For the same circuit, this one, I'm going to show you the three possible cases, data flow, the behavioral, and structural. But of course, again, I'm keeping repeating this again and again. This is the best one. Now, if I work with a signal, if I declare this as a signal, which I did here, I can write two statements. It doesn't matter which one goes first, because they are concurrent. And I showed you this examples before, right? So I could have written only one statement, XOR 2 out is equal A XOR B or XOR C. This is an alternative solution, so I can replace this with just one statement. Both solutions are correct. And then we can do it with a process if we want. But again, process, we use it when we do sequential circuits. So this is not the best solution. But if I want to do this, we can do it with this way. So ABC, and then we did this, yeah? This is the same code that I showed you before. This is so you need a process, and then inside the process you use sequential statement, which are the if, the loops, and the loops could be for, could be while, could be loop, just loop. And we have the case statements as well that you can use inside the process. We can do as well structural if we want. So we describe this as a component, and then we use it twice inside the circuit. And this is the solution. So this is the XOR gate. And then we copy this, copy paste, and then we just do the port mapping. So for the port mapping, do you see here? We declare this as, this is a signal. Here it's very important to use a signal, otherwise you cannot solve the problem. So I'm declaring a signal here, because when I do the port mapping, so A is connected, X is connected to A, Y is connected to B, and then Z is connected to what? It's connected to this wire. So I need to declare it. So this wire is an output from the first gate, and it's an input in the second gate, right? So we declare this, and then we can use it here, and then it's used here as well. So did you see it? So it is connecting those two together here. And that's it. So this one, you cannot solve it without declaring this wire. So you have to declare it. So it's very important to have the signal here. That's it. So structural, as I told you, so component is fine. I mean, I think it's good, and I hope you understood it. We will do more in the tutorial. Structural, again, this is not the best one, but we will use it again when we cover the which we will do soon, sequential circuits. I think that's it for this lecture. So this is the end of this lecture. We will do the tutorial next session, inshallah. So we stop here. I will see you next session anyway. Okay, no problem. Next session it will be anyway the exam, yeah. We'll do the tutorial, inshallah. Right. So that's it. So if you don't have questions, then we'll talk to you next session, inshallah.
Doctor.
Thank you, Professor.
Okay. Thank you.